Hello, I'm back, and today is still January 2026, and this is my second video. So as promised, today we have Pygmalion. So Pygmalion is a very interesting book. I don't think even most computer science PhDs and majors have even really heard of this, but it's actually a very critical piece of kind of computing history in general. And yeah, it's just very interesting. So let's get into it. So what is Pygmalion? So Pygmalion is the name of this PhD thesis of this guy named David Canfield Smith at Stanford in 1975. And basically, he subtitled it A Creative Program to Model and Stimulate Creative Thought, or a computer program rather, which sounds very grandiose, and it actually was. Like this is a very ambitious program, but keep in mind this was 1975, and even just like the basics of computing haven't really been established yet. So just even like very basic things can have a really big impact. Cool. Okay, so first of all, what is it? So basically he made a kind of operating system. It's a very early kind of operating system, and it was based on icons, right? So it's like this, right? So there's kind of a series of commands on the side, and there's kind of an open like whiteboard area, where you can actually drag and create icons and make kind of math equations and kind of simulations of circuits and stuff like that. And the really interesting thing about this is that the first half of this is very much structured like basically more of a novel or philosophy treatise than a computer science thesis, right? So he has sections titled like on creativity, or like how are creative thoughts structured, how they come about, and stuff like that. So just to kind of summarize, he basically says that creativity or creation comes about at the intersection of different fields, right? So he actually has a graphic of this that I'll find. But basically, if you have a field like say uh, planetary orbits, like astronomy and mathematics, in the 17th century, right? Then that intersection is what creates, let's say, calculus, right? Where Newton was trying to kind of calculate orbits, right? So like, why aren't they circular? How do orbits kind of change and things like that? And so he had to create a kind of a new kind of math because of that intersection of the limits of the intersection between astronomy and mathematics. Um, so just a lot of kind of that stuff. So here's the graphic, like that. And so basically, he says that at the intersection of these kind of various fields, as you go back and forth, as you go back and forth, that's where kind of like new creative ideas come from. And so he kind of has to kind of lay all this out because at this point, computing is very new. It's very much command line based, right? So you know, like those terminal computers where it's like a screen and like the text comes in like da, right? So it's like it's all text. It's very little visuals at this point, and so computing is very much just for like mathematicians and like very highly specialized technicians. But this paper and a lot of the innovations that kind of came along this kind of cycle were really what propelled computing to be what it is today, just like this ubiquitous visual thing that everybody uses. And so there's a lot of very interesting concepts that he kind of goes over while introducing this. Introducing this. Um, and so I'll just kind of go over a few of them, and then I'll kind of go over like the system and like his impact on the overall scene in computing. Um, I think the most interesting thing that I found was he has a brief mention of this branch of ancient Indian mathematics, where right, so mathematicians will know that a lot of mathematics is proofs, right? So you basically have to prove something is true. And so there are a lot of ways to prove something is true, right? Like there's mathematics by induction, by contradiction, things like that, right? So show A is true, right? Show A is true, but then maybe you have to show that A is uh, show that B is true, and if B is true, then A must be true. Or you have to show that A cannot be false, and so it must be true. Uh, Things like that. The mathematicians in the audience will know this better than me. But in ancient Indian mathematics, back when there weren't any like math, math PhD committees and stuff like that, they had this very interesting, purely geometric method of proving things. Where, for example, this is a proof of the Pythagorean theorem that's purely geometric, and there's only three images, right? And at the end, it just says, behold, right? So it's basically saying, hey, this thing is true. I will show you. And it shows it geometrically and just says, behold, this is true. Like that, right? Behold, behold. And I thought that was really interesting. Number one, because stuff like this would never work today, obviously. Like, this is not how you get, like, a PhD in 2026. Um, but also just because it works. And I think it speaks to um, a lot of the magic that we lost in, like, academia in general and, like, mathematics, like, specifically. Just, like, look how simple this is. Okay, granted, this won't work for, like, the Riemann hypothesis or stuff like that, but, like, just the fact that, like, look at how simple this is. And so the reason he mentions this is because, like, he introduces this concept to basically say, hey, this doesn't have to be complicated. Computers don't have to have, like, these extremely elaborate syntax structures and, like, these logic trees to be proper computing or proper. You know what I mean? And so he he, meaning Smith, the author of this paper, he basically introduces the entire idea of icons in this paper. And that's another concept, icons. Icons are very interesting in this paper. So before this paper, or just in general, the word icons did exist, but it actually mainly referred to religious icons, right? So if you are familiar with the Orthodox Church, icons are basically statues or paintings that represent holy figures, right? So let's say like a statue of Jesus, or like a painting of the Virgin Mary, or something like that, right? So it's like, and the key concept here is that the icon was set to embody some of the holiness of the figure, right? So a painting of Jesus embodies some of the holiness of Jesus, and therefore, if you harm the painting, then you are committing a sin, because it's not just a painting; it's a painting of Jesus, and you're actually harming some of the holiness, or you're committing a sin against some of the holiness of the actual holy figure, things like that. Um, and so the key idea here is that there is this visual representation of something, and there's an underlying figure, and it kind of embodies some of that, right? It is not that thing, right? So the painting is not Jesus. The painting is not Jesus, but the painting embodies some of the holiness of Jesus. And if you harm the painting, if you manipulate the painting in any way, then in some way you're kind of manipulating an aspect of Jesus, is the point. Um, and so Smith kind of uses that to introduce the idea of computer icon. So he actually has to kind of go out of his way to explain what an icon even is. But basically he says, yeah, like, an icon is not an actual computing concept. But if you manipulate the icon, then you are manipulating the concept behind it. So for example, in a video game, there is a picture of, like, a rocket in, like, Galaga. Um, if you move the rocket, right, if you move the rocket, right, the rocket is actually just a piece of code, right? So if you drag and move the rocket, or if you click the arrows and you move the rocket, you're actually not moving the piece of code, right? Like, the code is not affected, but you are indirectly manipulating the object that the rocket represents, right? Might sound a bit complicated, but let's give another example. Let's say you're dragging around an icon, or like a folder on your desktop, right? So you have, like, a photos folder on your desktop, and then you're dragging it around. You're not literally dragging around anything, right? You know what I mean? Like, you are all that is doing is changing a few numbers in the desktop to say, okay, the photos folder on this guy's desktop, instead of being in this position, it is now in this position. Yeah. And so maybe, like, it changes, like, the dimensions from, like, xy 1020 to, like, 3040 or something like that, right? So you're not actually dragging anything, but you are actually making a change. And so you might not be actually directly manipulating the numbers, but you are actually making a change by doing something that represents that change, not typing numbers, but dragging the icons. So just a lot of, like, that kind of, like, those kinds of like, analogies and metaphors are pretty much the foundation of this entire paper. And so I just found it really interesting, just because so many things we kind of take for granted in modern computing, and you kind of forget that they had to be invented, right? So he kind of goes on to basically have all these kind of very typical layouts, right? So you have, right? So each icon has kind of its own properties. So like a person, you have a name, a sex, and an age, occupation, address, stuff like that. Um, and so basically, he makes a form of like flowchart, even though he says that flowcharts are not great. Um, Let me explain. So okay, so it's not exactly a it's not exactly a flowchart, but basically, it's like in Pygmalion, in this operating system, if you combine 5 and 2, and if you drag them together, then I believe it just becomes 7, right? Like, you don't have a flowchart where 5 and 2 lead to 7. I believe 5 and 2 just become 7, or something like that. And so Smith, in the paper, he actually very much discourages flowcharts. He doesn't like flowcharts. And the reason he doesn't like flowcharts is because he says it's still a representation of logic, not the logic itself, right? So if you write 5 plus 2 equals 7, that's not the actual logic happening. That's not 5 and 2 being added. That's just a visual representation of how to do it, right? It's a recipe. 5 plus 2 equals 7. That's a recipe. It's not the thing actually happening, if that makes sense, right? So for example, like if 5 and 2 were added, 5 and 2 would no longer exist because 5 and 2 have been added, right? So in a right? So it's the difference between a recipe and actually cooking something, right? So if you have like a recipe for a cake that says, put put this you know put this in the oven for 30 minutes and then pull it out and then put like a cherry on top of it, like stuff like that. You have a step-by-step kind of guide on how to do something, and it does represent a cake, but it's not a cake. A cake is the actual thing that you have, right? So there's a step-by-step guide, and at the end of the guide, you will have a cake, right? So that's the recipe, versus you actually have a cake. Um, so that's the key difference. And so he spends a lot of the time doing basically what I'm doing right now, which is to try to explain, um, this whole idea of like iconic programming in like as human terms as possible. But this is in Pygmalion. Um, so basically he says flowcharts, boo, right? Like no flowcharts. He doesn't like flowcharts because he says they represent logic, but they are not the logic themselves, if that makes sense. Um, yeah, and so he has a lot of like paintings and like a lot of like uh, thoughts about art and creativity rather than equations and computers and things like that, which may be very surprising for a computer science PhD thesis, as you can imagine. But this is kind of how it goes. Um, and oh, another cool example. So he basically says, okay, right. So look at this image of kind of like this Tetris-like figure, right? So he says, imagine someone told you this sequence of words, right? Up, left, down, right, down, left, right? That's very hard to like remember on the first try, right? Up, down, right. Oh yeah. Up, right, down, left, right? It's very hard to remember just like verbally. But if I were to show you this picture, which is basically what that does, up, right, down, left, right? This picture is extremely easy to remember, right? So like the visual core of the brain is way stronger than the verbal core of the brain, right? He calls words, I believe it's Phrygian or something like that. Basically, words are like the highest abstraction, and it's very useful because it allows for a lot of abstraction, but ultimately it's not that tied to reality, which is why people have to learn all this kind of grammar, which is why programming is so hard, is because it's so just detached to the reality of things, and it's not as conducive to actually allowing people to use computers the way that people might be able to use computers. Cool. Okay, so anyway, you should read Pygmalion. Honestly, even if you're not like a computer science PhD, this is just very interesting in general. And so I just highly recommend this to anybody. It's available online, like the full thing is online for free. And you can also buy it if you're a weirdo like me. Um, okay, so that's Pygmalion itself. The impact. This guy, his advisor was this guy named Alan Kay, who was a professor at Stanford, and he also worked at Apple as, I believe, a user interface person. Very, very influential, and his ideas have kind of really propelled computing for the past few decades. And so his students include a lot of people at Xerox PARC. So I believe this guy was at Xerox PARC too. But Xerox PARC was basically a research lab in the 1970s where so much of modern computing was created. You know, like the mouse. The mouse wasn't literally at Xerox PARC, but I'm condensing a lot of things here. The mouse was created at kind of like an early precursor to Xerox PARC at SRI. The graphical user interface, the GUI, right? So like the idea of windows and folders and icons, that was created at Xerox PARC. Ethernet was created at Xerox PARC. And very, very famously, Steve Jobs and Bill Gates both visited Xerox PARC in the 1970s, and they kind of stole like the main idea of the GUI, and they stole it for the Macintosh and Windows, right? And that's kind of how it became so ubiquitous. Still to this day, Xerox gets kind of very unfairly criticized for not properly capitalizing on the innovations in their own research center. But it worked out pretty well for the world because of Mac and Windows. But yeah, again, like pretty much all computing we know today, even this YouTube thing that we're apparently doing right now, right? Like this entire idea of screens and windows and icons and these draggable objects on a two-dimensional kind of like plane, all of that is basically a child of Pygmalion, right? It is a child of the idea that you can have visual elements on a screen that represent items but are not the item themselves, right? You can manipulate an icon, you can manipulate a window, right? But you don't have to actually change the code. But if you manipulate the actual icon, then you will change the code, right? You don't need to know how to code in order to use Chrome or to use YouTube or to watch a video, right? Because all of that is done for you, right? Because of this abstraction layer. And so, okay, final thoughts on this is AI. Kind of inevitable that we're talking about AI, but how will this change in AI? I'm not sure. The big pattern so far in, I think, this kind of world was that every metaphor that we've had so far for computing has been thoroughly in the realm of tools and kind of tools and desktops and kind of very perfunctory things, if that makes sense, right? So the desktop, windows, icons, like the paintings, like scrolling, right? Like literally like a medieval scroll, are all tools that people use, and we've digitized those tools as a metaphor. And so now we have like computers that kind of replace all those things, like calculators and stuff like that. With AI, I think so many people are already thinking of AI as like this live sentient thing. You know what I mean? Right? So like people talk about ChatGPT like, oh, ChatGPT, he understands my problems, or like Claude is so smart, stuff like that. It's so live that I think a lot of the metaphors that will come from either number one, child psychology, or number two, biology. And I think that's already happening, but it's very difficult to see as of right now what form that will take. You know what I mean? So in some sense, that's already happened. The predominant kind of AI paradigm right now is the neural network, right? The neural network, if you don't know, so the neural network is basically this like idea that the brain is made out of thousands of tiny little cells called are these cells? Thousands of tiny little things called neurons. And the brain works by sending signals between those neurons, and that's how basically how you think. Um, and so modern AIs like ChatGPTs, or rather like the transformers, right? So GPT is generative pre-trained transformers. So the transformers are based on neural networks, where basically they have artificial neural networks, and they send thousands of little signals between them, and that's how they quote unquote think, right? So it's directly inspired from the brain, like the human brain. Um, and so already these machines are made with by using parallels to biology, right? And so I think it's only natural that whatever metaphor for human computer interaction kind of comes next will also come from biology. What kind of biology? I have no idea. Um, like how do humans interact with one another usually? We talk to each other. You know, uh, we I guess we like touch one another. But even that is so like abstract. I mean, right? It's like you also touch a computer like already. You know what I mean? Like you give us like you work together. Um, but you have like a desk and like you collaborate like on a desk together. Um, you send each other text messages. Like uh, only professionally. I mean, saying like how do people professionally work with one another like on a daily basis? Um, I think that's the big thing to kind of tackle now, right? Um, and so like all these AI agent companies are trying to make AI employees and things like that. And and who knows who'll win? But I think right now I'm just very very curious to figure out or to kind of discover or to invent even um, how the Pygmalion will affect the next generation, or what the next generation Pygmalion will be. Um, by the way, last fun fact is that Pygmalion was named after this figure in Greek mythology. He was a sculptor, and then he created a female sculpture, and then he fell in love with the sculpture, and so he wished I believe it was Aphrodite to bring her to life, and they got married. And so that this was kind of inspiration about the name. He wanted basically David Canfield Smith, the author of this paper, he wanted computers to be alive, and he wanted be alive and more kind of dynamic than like the static like type text terminals of his day. Um, yeah. That's so that's pretty much all the thoughts from me. I'd be curious as to whether there are any fun ideas about how the future of human computer interaction kind of happens. But yeah, what will the next Pygmalion be? And who will the next David Canfield Smith be? You know what I mean? How do what will the next desktop scenario be? And is there another paradigm beyond this? Like beyond AI, is there another kind of paradigm shift to happen in computing? Like, is this it? You know what I mean? A lot of questions. And so I'd be curious to see what you guys think. For the next one, for the next video, what should we do? I'm just looking around at my very disorganized set of books. Um, oh, okay. Well, so I do have this book, but it kind of covers a lot of the stuff that we already talked about. It's basically about Xerox PARC. So okay, so next time, I don't know. So you guys will find out what the next video will be. When the next video actually comes. All right, see you guys.